All right, so it's my pleasure to introduce Nihar Shah. Nihar is an associate professor, I need to read this, in the machine learning and computer science departments at Carnegie Mellon. His research focuses on evaluation of science and the science of evaluation. This is not a riddle. His work has been used in the review of many places, over 100,000 papers and 1,000 proposals across over 200 venues. He's a recipient of the Young Alumnus Medal from the Indian Institute of Science, a JP Morgan Faculty Research Award, a Google Research Scholar Award, and an NSF Career Award, and the David J. Sacrison Memorial Prize from UC Berkeley. Papers authored by him have won awards from HCOM, AMAS, IEEE data storage, and so on.
I wonder who the co-author was in that AMAS paper. Research. Yeah, thank you so much, Jingyan, for hosting me, and thank you so much all for coming. So today I'm going to tell you about randomization in decision making under uncertainty, and in particular, this is motivated by research funding decisions. Okay, so now in case you're not familiar with research funding, like you can substitute that with, say, NeurIPS reviewing or admissions, etc. All right. So research funding. So how does the traditional or typical research decision process work? Well, researchers will submit proposals, and let's say that there are a total of n proposals submitted. And then the funding agency has budget to support k proposals. So throughout the talk, I'll ask you to remember these two pieces of notation: n, the number of submitted proposals, and k, the number of proposals that is going to be chosen. Right. Now, in traditional processes, what happens is that each of these proposals is reviewed by experts, and then there is some panel discussion for many, many hours or maybe even days. And at the end, everyone will decide, oh, we think these k are highly competitive, we'll fund them, and then the others are not funded. So it's a deterministic decision. Okay. Now, there are a number of funding agencies worldwide which started saying that, well, this process has a number of problems. For example, there are known biases against novelty, novel proposals, high-risk proposals, etc. There are known biases against certain author demographics, and they say that the traditional ways of doing it discourages novel proposals, discourages proposals from these demographics. Furthermore, there are a bunch of experiments which have found that the panel deliberation and decision process is very arbitrary. And so we are also wasting a lot of time. For these reasons, a number of funding agencies around the world have started introducing randomization in their proposal decision process. Okay. So next, what I'll tell you is how they are currently doing this randomization, and then we'll discuss what are potential issues with it and how to address it. Right? Any questions? Feel free to interrupt me if you have any questions at any time. All right. So now, let me start mentioning how this randomization is done. And what I will do is I'll use this picture as a running example. Is this too far away for people on there? Should I draw it in the middle? Yes, no?
Looks fine to me.
It's okay.
Looks fine? Okay, great, thank you. I'm going to use this picture as a running example. Okay. So in the traditional funding processes, what happens is the following. So let's say there are 8 submitted proposals, n equals 8, and you can fund 3 of them, k equals 3. Then after all the reviewing and deliberation and so on, you'll make a chart of this form, where on the x-axis, I have different proposals, and y-axis is the perceived quality through the review process. Okay. Now, for the traditional proposals, just focus on the dots here. And so what this says is that this proposal number 1 has a perceived quality which is this high. Like this could be highly competitive in NSF speak. Proposal 2 has this perceived quality, and so on. And then in the traditional funding process, once you get this, you'll pick the top K. Okay, so that's the traditional sense. Now, what many funding agencies in the randomized setting have started to do? Yes.
What's the in the traditional sense? What is the bars in the traditional sense?
Yes, in the traditional sense, there is no error bars.
Okay.
We'll use these error bars in a moment for the randomization part. Yes. So in the traditional sense, we all discuss. We are the panel. We'll discuss and we'll say, hey, Jingyan's proposal is highly competitive. So Jingyan proposal is a dot here. All right. Okay. So now let's look at the randomization part. And in the randomization part, we'll break this into two different parts. So first, the reviewing is done, and then you come up with point estimate plus intervals around it. Yeah, question?
So is underlying, and maybe you will get to it, so feel free to click, but is underlying kind of model here that there is a true underlying scalar quality of proposals, and the reviewing scores are noisy measurements of that?
That is correct. So for example, I'll describe the Swiss NSF model next, and they have exactly this kind of an assumption through which they'll generate these. Okay. So I'll describe their model in just a minute. Other questions? All right. So what they do is first come up with point estimates as well as intervals like the picture on the right. Now there are several ways to do this. One popular way is what was proposed by Swiss National Science Foundation. In this very nice 2022 paper by Hare et al. So I'll describe their model to you. Their model is very simple. They assume that each proposal has some true quality. Let's say proposal J has some true quality theta J, which is unknown. They also assume that each reviewer I has some true bias B star I, which is also unknown. So both are real values. And the bias is representing whether a reviewer is strict or lenient. Okay, so if B is high, it means the reviewer is strict. If B is negative, it means the reviewer is lenient. And then under their model, the rating given by reviewer I to proposal J is simply theta star J plus B star I plus Gaussian noise. Okay, this is their model. And then they have some hyperparameters on these and some priors on these as well. Okay, so hyperpriors on these and priors on these. And that's their model. And then given these ratings, they'll come up with point estimates and credible intervals for theta star J's. And that's how they come up with that picture. Okay. Any questions?
I'm curious, just like roughly how many proposals rated by each reviewer in their system? Just trying to get a sense of.
Yes. Yes, great. So the total number of proposals is several hundreds, and in their setting, what happens is, in the Swiss NSF setting, what happens is there are some reviewers who will fully review the proposals, and then there's some panel where everyone will discuss and everyone will rate. So everyone who does not have a conflict of interest with the proposal will rate it. So it's a very dense matrix. Yes.
Well, they have like some kind of pool of money, where the money comes in.
Sorry, I didn't follow that.
They have like, you send a proposal, yes, they have to grant some money to you, so they have a limited funds.
Yes, they have limited funds.
So
yeah.
where this comes into the play?
Yes, where does the limited funds come into play? That's a great question. So first, like through this, they'll come up with that picture, and after this, there's the decision-making process, which I'll describe in a minute, where the limited funds will come into play. Yeah.
This is causing me to think about the Netflix challenge. So reviewers could have biases toward genres,
Yes.
right? And the proposals could be in genres.
Yeah.
And is that analysis, that's not in your equation?
No, so they don't have that, and I've not seen that being done anywhere else either.
Well, for proposal reviews, you mean? I mean, it is done in other contexts. You mean for
Oh,
proposal
yeah, and
reviews?
proposal or paper reviewing.
Yeah.
In proposal or paper reviewing, I haven't seen that. One possible reason is the following, that in many other proposal and paper reviewing settings, including say NeurIPS, etc., you have much more sparse data per reviewer. Per reviewer, you have like 3 or 5 papers being reviewed, and each paper is reviewed by 3 or 5 reviewers. And therefore, you have like, if we have to model more things, then you will have far more parameters, and potentially there could be problems. But yeah, I haven't seen it in this context. Great, other questions? All right, questions? Yeah? No? Okay.
Oh, sorry.
So, based on this model, they come up with this picture. Now, other funding agencies have other ways of coming up with this picture. For example, the simplest thing to do is take these intervals, the lower and upper intervals, are simply the minimum and maximum score that this proposal received from the reviewers. Okay, things like that. So, there are various ways in which one could generate these pictures. Okay. Now, our focus here is not so much on how to generate this, but on what to do with this. And this brings me to the second phase of what they are doing. So in the first phase, you get these point estimates and intervals. And then in the second phase, you make the decisions. Okay. So now I'll describe how they use that picture to make their decisions of choosing the K proposals. So now I'm going to describe 2 popular approaches. The first approach is that followed by the Swiss National Science Foundation. And here, first, they do the following. They order the proposals according to the point estimates, and then they look at the kth proposal. So here k equals 3, so look at the third proposal. Okay, and you look at the point estimate of the third proposal, which is here. Now, you create a funding line at this value, okay, at the point estimate of the kth proposal. Next, what you do is look at which proposals are entirely above the funding line. In this case, it's proposal 1. And this is accepted with probability 1. Now look at which set of proposals are entirely below the funding line. Here is 5, 6, 7, and 8. And so these are accepted with probability 0. Now you look at, well, how many more can we fund? K was 3, we have funded 1, so we can fund 2 more. And how many are left? 1, 2, 3 are left. So from these 3, you choose uniformly at random with probability 2/3 each. Okay, this is the Swiss NSF decision-making approach. Okay, questions?
Why?
Why? It seems reasonable enough, and they thought it was reasonable. I think it's decent enough.
I guess the main question is why take all these in probability that ignores their interval? Like it seems very discontinuous, right?
Yes, it is highly discontinuous, and I mean I'm going to complain more about this, but at first I think it's decent enough.
Is it and again, maybe we'll talk about it, but is it clear what the underlying numerical objective is that any of these methods, does it make sense to define one?
Yes, so the Swiss NSF paper has a certain objective that they specify, and they look to optimize under this model. So they try to do a maximum a posteriori probability estimate of that. Yes.
That's a bit different. Let's say that
Okay.
you have magically post hoc access to the true Q stars,
Mhm.
and then you have a set of selected K proposals at the
Yes.
end. Is there some number that you can compute which says how good, what is your regret in some sense?
Yeah. There's nothing that's like nothing that's like widely accepted and so on. Like you could do simplest things like how many of the true top K did you pick, or you could have more like regret values, that is true the Q stars of the true top K minus the Q stars of what you chose, things like that.
Which reflects that maybe the next K proposals are almost as good as the top K, so it's not a big deal if you don't pick the top K, for example. The second one you said, let's say all of the top Ks are Q of 100 and the next K are 99.99.
Mhm.
Right? Then it doesn't really matter.
Right.
And the first loss would be, if you pick the second K, the first loss would be terrible, the second loss would be fine.
Yeah, and there's no kind of widely accepted thing that we should do this over that.
So I'm curious, so when people propose something like this,
Yes.
they describe it and then how do they make a judgment whether it is good?
So as I said, they have certain specific metric which they look at, which is some combination of like you want to do true top K, and then what you're looking is how much is the ranking error that you're making, not the error in terms of the value.
Okay, so they specifically then pick the ranking loss.
Right. Yes, they have ranking loss. So and in general, like the loss in terms of value is perhaps a little harder because the y-axis scale may not be linear. Typically, you have like in Europe's you'll review, you'll have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, but it's not really linear. So if you're just looking at mean squared error, it can get messed up.
But here you are assuming this very strong linear structure.
Well, they are assuming a very strong linear structure.
With real valued scores, which is also not, doesn't presumably.
I agree with you, and that is my complaint as well. Yeah. Other questions, comments? Yeah.
I guess so. Part of the initial motivation that you gave was around the like things like bias against novelty and stuff like this. Is this kind of proposal trying to do anything about that, or?
Right. So not necessarily this, but what they're saying is that, well, now that you have randomness, what often happens is, for example, that the proposals which are high risk, potentially high reward, because the reviewers are conservative, they consistently get pushed just below the bar. But now if you are randomizing, then there is a chance that they'll get included. So that model doesn't necessarily reflect it, but the fact that you're doing randomizing is kind of reflecting.
This might be slightly out of scope, but like you were saying, this example of you're trying to encourage maybe more novel or just a wider range of selection, like is there any like this is maybe the motivating assumption and then you change how you pick stuff, but like do they have ways of like once you pick a new set of things, you have a way of telling if like the kind of new set that you've picked is like better in these ways you care about, and like is
Yes.
that hard? I assume that's hard to.
But in some cases they have done measurements where they've looked at, for example, things that are easily measurable, like demographics, right? How many female PI proposals were accepted, things like that. And what they've found is two things. One is that with this, like a greater fraction of female PI proposals were accepted, and then subsequently a greater number of female PIs submitted proposals. So it's kind of is meeting some of their goals.
Do you have make any assumption what bias independent of the quality, how they are related to each other?
Yes, so in their setting, bias, the B star and theta star are completely independent.
Independent?
Yeah.
But it's a very strong assumption.
I agree with you. I mean, this is not my model. This is what the Swiss NSF is assuming. I agree, like we can make it more and more complex as long as we have data to do something with it. Great. Other questions? All right, so this is one approach, the Swiss NSF approach of making the decisions. Second approach is what's called randomize above threshold. So this is a very simple approach in which you do the following. So just like Swiss NSF, you define a funding line. But now, this funding line is defined before the review process starts. So it's independent of the data. Yeah. So let's say that this is your funding line. And now you choose some statistic of the perceived proposal quality. The simplest statistic is, let's just say, the point estimate. Okay. You could choose, say, the lower confidence or upper confidence as well. Let's just go with point estimate for now. Then what you do is the following. Just look at the proposals whose statistic is below the funding line. You'll reject them. And then amongst the rest, you choose uniformly at random. So amongst these 6, you'll choose each of them with probability half each. Okay. This is randomized above threshold.
Do the people who are making doing the ratings, making the reviews, know the funding line?
Yes. Yes, and there could be some effects based on that. I agree. Yeah, but this is like beforehand. It's publicly known.
So if we, I don't know how to think of the bars, but if we can think of that as, say, 4 people ran a proposal, and you know top rating to bottom rating. So then, in some sense, it's like you're taking the max. In other words, you're rating what did the person who read it, who liked it the most, what did they think?
Yes.
And if at least one person who read it likes it enough, it goes in the pot. So that's a way I could think about it.
Yes, if you're looking at the upper interval for the randomized above threshold, then exactly, yes, that's a perfect interpretation. Yeah. Great. Other questions?
Like a question. So any time when you like if the proposal it has fashion, like now artificial intelligence. If it's no artificial intelligence, it will not get any. Like almost 99% that will not get any funding in this area, right? So where did it come into play this like fashion, like what?
Yeah. So what I think what you're saying is like you might want some diversity of proposals that are accepted. Right, and that's something that I haven't seen them explicitly do, but implicitly sometimes they have tracks and stuff, which they're doing. The questions? All right. So now these are 2 popular ways in which this randomization is done. So next, what I'm going to discuss is a few drawbacks of these approaches that we found when we started looking at it, and then I'll describe our approach towards this problem. So at this point, we're not going to worry about how these incentives and estimates and intervals came about. We're going to abstract it out, and our focus is on the decision process. We're assuming this picture is given to us. We're looking at the decision process. Okay. All right. So when we started looking at these, we found a number of potential drawbacks amongst the current approaches. So I'll describe these to you. One is the following. So for the Swiss NSF case, now I haven't described the Swiss NSF full model to you in detail, but what we can show is the following. This is not a difficult proof that So you can show that like, if you stare at the Swiss NSF full model and objectives, then you can show that in fact choosing deterministically itself is optimal, okay, for their objective, right? So I won't go into this detail because I haven't described the full model to you, and that would be a digression. A second thing that I'll mention again about Swiss NSF is non-monotonicity. So what do I mean by this? So let me define what do I mean by monotonicity. Yeah. So let's say that you have a budget of K, and under the scheme you care about, you assign probabilities for all the proposals. Now let's say the government comes and says, hey, we got this little more money for you, and your budget has been increased to K plus 1. So under this, by monotonicity we mean that the probability of any of the proposals getting funded should not decrease when the total funding increased. Any questions? Yeah. And turns out that Swiss NSF is not monotonic. So here's the example. So now again, when K was 3, we had this funding line that was defined by the third proposals point estimate. And so these 3 proposals had a probability of 2/3 each. But now, when the funding line changed to K equals 4, which is this one, now 7 and 8 were rejected, 1 was accepted, but now you were choosing 3 out of these 5 uniformly at random. And so the probability of all 5 is 3/5. So in particular, the probabilities for proposals 2, 3, and 4 go down from 2/3 to 3/5. Any questions?
For the first part, when you say optimal, because you were saying it before about there's also like time deliberation. So when you say optimal here, is that just like kind of in terms of like solutions you pick rather than
Yes,
time
in terms
spent?
of the solution you pick. Yeah, not the time spent. So when they are doing this modeling, they have a specific model and a specific objective in terms of which solutions did you pick. And I'm specifically with telling with respect to that.
Did they say anything about like in terms of time spent if their proposal was like, much faster or not?
I didn't see that in their paper, but there's another funding agency which has reported significant reductions of time. Other questions? Okay. So Swiss NSF is not monotonic. A third point that I'll mention is sometimes in some specifically in the randomized above threshold case, it can do something which I think is unjustifiable in the sense that if proposal A dominates proposal B, then what we want is that if B is picked, then A should be picked. This is what we want. So if from the review process you have sufficient evidence to believe that proposal A is better than proposal B, then we want to ensure that if B is picked, then A should also be picked. Question? Yes.
I'm a bit confused. What do you mean by dominates? And second,
Yes,
you say picked.
I'll mention that.
When you say picked, you mean
Chosen, like when in the final sampling.
in the final, at the end, not like the probability. So
Yes.
or-
Yes, at the end when it's chosen. Yes. Okay. So randomize above threshold fails this, and that's easy to see. So let's say that you still have k equals 3 and you had this funding line for randomize above threshold and you're looking at just the point estimate statistic. Then here it assigns probability of half to each of the first 6 proposals. Right. But now you stare at proposal 6 and stare at proposal 1. Now by domination I mean that the interval of 1 is fully above interval of 6. But if you don't sample carefully enough, then there is a non-zero probability event that you pick 6 and you reject 1. That's what I mean by this. Any questions? Okay. So in addition to these, there are several other social choice theoretic axioms that these violate, and I'm happy to discuss those as well offline. So I'll pause here for any more questions because this is where I'm done complaining about the prior works. Questions? Okay. So now I'll discuss. Which are questions?
So just a question. So in this first proposition, you have not specified the objective yet. So you're just saying optimal, and you're trying to.
Yes. So I've not described this in more detail. It's there in the paper, but I won't have time to describe it. But yeah, like there is a well-defined objective and complete model specification under which this is true.
Also for the proposition 3, what happens with the other method that Swiss NSF is using?
Swiss NSF does satisfy this. Yes.
Can you just quickly?
Yes. Why does Swiss NSF satisfy this? So if, let's say, proposal 1 dominates proposal 6, right? Then now let's see where the funding line could be. If the funding line touches 1, then it is strictly above 6. So 6 is rejected.
I see. This is because your definition of domination is that it should be strictly above.
Perfect. Perfect. Okay, other questions? All right. So now I'll describe our approach. And in our approach, the way we are thinking about it is that we want to choose k out of n proposals such that any certainty in the data should be respected in our decisions, but any uncertainty in the data should be captured in the randomness, okay, at a high level. In more detail, we are going to put 2 conditions. One is what we call ex post validity. And ex post validity is exactly this. We are going to put this requirement. That if the interval of some proposal A is strictly above the entire interval of another proposal B, then if we are finally choosing proposal B, then A should also be chosen. Any questions? Right. So now let's say we impose this condition. Even then, there are many choices of k proposals which satisfy this condition. So at this point now the question is, well, how do we assign the probabilities? There are many possible ways. And towards this, we impose a second condition which we call ex ante optimality. So what do I mean by this? So now the goal was to select the true top k proposals, right? But so the goal was to do that. So now let's look at the following. Let's suppose that P1 through Pn are the marginals of the probabilities of picking the n proposals. Let's say that's P1 through Pn. Now, we wanted to pick the top k proposals, and so the expected value of the utility under the marginals P1 through Pn is just the sum where I is in the true top k, whatever true is, Pi. This is the expected utility. The utility would have been an indicator that I is chosen, and the expected value is Pi, the probability it's chosen. But now, what is this ranking? Right? We don't know the true ranking, we have no idea. And so our approach here was to take a worst case. So we take a min overall valid rankings, where by valid I mean ex post valid. So we are taking the worst case approach over all possible rankings because we don't know the true ranking, and we are considering all rankings that satisfy ex post validity. Yes.
Like, what do you mean by ranking? You just mean an assignment of probability to each?
I'm sorry. So by ranking, I mean just an ordering of the n proposals. And what we are saying is that we don't know what is a true ordering of the n proposals in terms of the quality. And so we are taking the worst case over all possible orderings that respect the data in terms of ex post quality.
Is that the same? So I can think of another definition of valid, which could be, so for every proposal you have an interval. So for all ways of picking a point in each interval and then ranking according to that. So for example, that first thing, the ex post validity, says that all of those rankings should have the property, or no, there should exist one under which you pick the top k, right? Because, right, so in some sense it's like the best out of all of those, you should have actually picked the top k, right? So,
I think this is
that
the same as what, I think it's the same as what you're saying.
okay.
Yes, I think it's the same. Because under your definition, if A dominates B, then no matter what point you pick here and here, this will be ranked higher than this.
So good. So I can think of perhaps the first condition is saying best case over valid rankings, I've got optimal. Because if I didn't have that, there would, and then the second one is worst case, I'm doing.
Yeah,
okay.
yeah, I think that's equivalent. Yes, yes. Right. And so this is the objective I want to optimize, and so I'll do a max overall P1 through Pn, which sum to k. Any questions?
What is K? Is the last one sum? What is the K?
Yes, k is the budget, the number of proposals that can be chosen. Because since we can choose k, the probability should sum to k. Alright. So now, overall, our approach is the following: that through ex ante optimality, we will get the marginals P1 through Pn, and then we want to sample from it so that you have these marginals and it satisfies ex post optimality, ex post validity. It's important to note that ex post validity is a property of the joint distribution, right? Because it's talking about pairs of proposals. So it's a property of the joint distribution, whereas this is only talking about the marginals. So in the next few minutes, I'll talk about how we go about solving this. The first part is something I won't go into the details because it's more involved, but then I'll describe a couple of clever tricks. Questions? Right. Okay, so at this point, the first question is, well, how do we solve this X anti-optimality? And when we started looking at this, we started looking at literature, and we found a lot of very closely related problems that were NP hard. For example, the problem of finding a minimum weight fixed size ideal. That's what it's called. It's very close to this, but that's NP hard. Right. However, that said, this has certain structure, additional structure, through which we were able to design a polytime algorithm, specifically a quadratic algorithm. Okay. I won't have time to go into the details of this because it's more involved. Okay. But at this point, let's assume that we have solved this and we have an X anti-optimal P1 through Pn. Any questions? Okay. So now we have some X anti-optimal P1 through Pn. So these are marginals for picking proposals 1 through n. And now what I'm going to describe to you in full detail is how we actually sample the proposals so that the probability of any proposal I being picked is exactly this optimal PI while respecting ex post validity. That's what I'm going to describe to you in the remaining 10 minutes. Questions? Okay. So now first let's see what can go wrong if we do it naively. And let's come back to our picture on the right. So let's take this picture again, where we have n equals 8 and k equals 3. And now, when we solve this, one optimal solution is where the probability for proposal 1 is 3/4 and the probability for 6 is 3/8. And there are some other values in between. But now, if we naively sample, then there is a chance that proposal 6 is accepted and proposal 1 is rejected. But since 1 is strictly higher than 6, that choice will violate our requirement of ex post validity. Any questions? Okay. So now the question is, what do we do? How do we address this? So here is our approach towards doing that, and it's a simple trick that we were able to do. So we are given X anti-optimal marginals P1 through Pn. And what we will do is the following. Our approach is convert these to different values, and I'll tell you what we do in a minute. So that they have two properties. Okay. So we'll take the given P1 through Pn, which we obtain by solving this optimization problem. And then we're going to modify them so that, number one, they continue to be optimal with respect to this. And number two, that any sampling that any arbitrary way you sample, as long as you respect these modified marginals, it will be ex post valid. Okay, so we are going to modify the P1 through Pn so that it has these two properties. And so if we can ensure it has these two properties, then they are ex ante optimal and ex post valid as well. Any questions?
I guess you can't do the usual trick of just pick a random number between 0 and 1, take all the PIs bigger than that number, which would get, because you need to pick exactly k things.
Yes, we need exactly.
You can't just.
Yes, perfect. All right, so how do we do this? So here's our algorithm. It's a simple algorithm. I shouldn't have deleted this. It's a simple algorithm. So I'll read the algorithm and then we'll actually execute it on this example. So the algorithm is simple. You take two variables. One variable is b, which goes from right to left, and the other variable is a, which goes from left to right, from 1 through b minus 1. And then for any pair a and b, you see, does a dominate b? If yes, then just move mass from pa to pb until either PA is 1 or PB equals 0. So let's execute it here. Alright. So this was our picture, and our variable B goes from right to left, and then A goes from left to right. So let's just say at some point, this proposal 1 is A, proposal 6 is B. Now we'll check. Does A dominate B here? Yes, it does, right? A's interval is strictly higher than B's interval. So now we'll transfer mass from PB, which was 3A, onto PA, which was 3/4, until either this becomes 1 or this becomes 0. Yeah. So in this case, we'll transfer a mass of 1/4, and this becomes 1, this becomes 1/8. And that's it. That's the algorithm. Now, why does this work? Well, let's see. Are there any questions about the algorithm? Okay. So why does this work? So first, let's look at ex post validity. Okay. Why is it ex post valid? So remember, if any A dominates any B, then we have made sure that either PA is 1 or PB is 0. Okay. This means that if B is picked, then A has to be picked. Right? Because either PA is 1 or PB is 0, one of these has to be true. Which means if B is picked, then A must be picked. So just by this property, we have ensured ex post validity. Questions?
So I'm still trying to understand. So there's no explicit stopping condition here. So you stop as long as you can still.
Yes.
So
you can keep transferring mass until.
So you'll necessarily end when all the when.
No. So what you will end when for every pair where something dominates the other, you satisfy.
Only if it's dominate, right? So okay,
Yes,
okay,
only
right. So you get a bunch of things that are not dominant.
Yes, perfect. Okay. So this is why it satisfies ex post validity. Okay, because PA has to be 1 or PB has to be 0. One of these two has to be true. Now, why does it satisfy ex ante optimality? Okay. So to see this, let's look at the following. Again, look, suppose A dominates B. Then, in any valid ranking, A will be ranked higher than B. Okay, that's how we define valid rankings. These are rankings which satisfy ex post validity. Right? So because A dominates B, in any valid ranking, A is ranked higher than B. So now if we look at this objective, and see that if B is in the top K, then A also has to be in the top K. So consequently in this summation, if PB is here, then PA is also there in this summation. And so any movement of mass from PB to PA does not change the value of this summation. Okay? Any questions? And hence, yeah.
I'm confused about one thing. So you had initially P1 to Pn which sum up to K.
Yes.
And now when you are transferring mass, are you talking about the normalized versions? Or?
No, normalized. So they still sum up to K
Okay.
because, and we have them to sum up to K because you want to choose K proposals, not one. Right? So by this mass transfer, this objective never reduces, and hence this is also ex ante optimal. So now we have devised a way to generate P1 through Pn, which are marginals, but any way you sample from it, it satisfies both ex post validity and ex ante optimality. Now the final thing in the algorithm is how do you actually sample? And this is a very cute and very simple algorithm by Maddow in 1949, which we use. Okay, it's a very cute algorithm and I really like this. So what you do is the following. You make a big rectangle. This rectangle is of length k, okay, 0 to k. This rectangle is of length k. Now, you mark length p1 here. Then you mark length p2 here. Then you mark length p3 here, p4 here, and so on. Okay. At this point now, you draw a random variable u uniformly at random from 0 to 1. And then what you do is the following. So see where u lies in this. Let's say u lies here, mark that. Now identify where u plus 1 lies, mark that. Okay, let's say it's here. Where does u plus 2 lie? Maybe here. Mark that, and so on, till you have u plus k minus 1. Okay. Now you look at, now here is how you'll choose the proposals. For proposal 1, look at P1's rectangle. Is there any point marked here? No. Rejected. For proposal 2, look at its rectangle. Is there any point marked here? Yes. Accepted. Proposal 3, is there any point? Yes. Accept. Proposal 4, is there any point? Reject. And so on. This is it. Okay. Very cute algorithm.
Why do you need this? Why not? I mean, why do you need this and not just sampling with probabilities k times without replacement probabilities proportional to pi? Wouldn't that give you the same distribution?
Okay.
So you divide by k and sample k times?
No,
You want exactly k.
Yeah, just sample k times without replacement, each time with probability proportional to the pi's.
But what is proportional?
Yeah.
You take pi's, divide by
You're
k.
saying do some normalization.
No.
You divide by k, take a random
No, not divide
uniform
by k.
variable
Why
to
divide
zero.
by k?
Because then it
Well,
will
at the
be
beginning
equal
in
to
k, but the next step will be not by k. Whatever. Just I mean, yeah, I'm just.
Oh, okay. Get your number uniformly distributed between 0 and k.
No, maybe
You're
we can come to
overthinking
that.
it. I feel like you're overthinking this.
There are various ways of sampling, and this is one cute way.
Okay, but I just need to. I need. It's
You
not
need
that I
to sample,
I
sample
don't need some
k, satisfy
complicated
this
property
margin.
for the sampling. I just need to sample the probability proportional to that. Right?
Perfect.
Without
You want probabilities that are exactly these,
Yeah.
and you have to choose exactly.
Yeah. Okay.
Right. You could just flip a coin for the first guy, take it or not take it, and then renormalize.
Yes, you can keep. I mean, there are various ways of doing it. Like this is one very cute way, and that's why I told you about it. I really like this. I mean, and this is not something we developed, it's from 1949. Yeah. So some final comments. So on the empirical side, like I described the theory, and this entire thing is order n square, computable. But from a practical point of view, it's also practical time that we ran it on 10,000 proposals, and it runs on conventional laptop in under 5 minutes. And we did a number of semi-synthetic experiments to measure the quality, and it turns out that it does quite well under the objectives we care about, and this same algorithm does very well also under the objectives and the models that they had specified in Swiss NSF. Okay. So while of course we are optimizing our thing and it will do well on our objectives, it simultaneously does as well as any other algorithm, even on the other models and other objectives that people have proposed.
Sorry, I'm a bit confused. You have various, when you say objective, I mean, you had various requirements here. This is what you mean by objective? Or you have some...
by objective, I mean this objective. So this objective is something that we proposed, and obviously we'll do well on it in experiments. And we will satisfy this. But then what we said was, okay, let's keep this aside because we optimized for it. Let's look at what they cared about in their paper, and then let's see how our method compares with these other methods on what they care about, and it gives a similar performance. So, in other words, while these worst case kinds of approaches are often very pessimistic, in practice, here it did not appear to be that pessimistic. So I'll stop here, and yeah, I'm very happy to take any more questions.
So it's past 3. If you need to leave, feel free, but we can take maybe 1 or 2 questions. And maybe before that, let me make an announcement. So Nihar will give a guest lecture in my class at 3:30 behind this wall. So, and there will be slides if you're wondering. So if you're interested, feel free to join.
Unorthodox slides for the class, but for a colloquium. Good question. So if you wanted to extend kind of the way of measuring quality proposals to multidimensional scores, so to speak, let's say feasibility versus importance, do you have any thoughts about if any of these approaches can translate to that?
Yes, that's a great question. Actually, in the setting without randomization, there's already been a bunch of work on this question in the context of both paper and proposal reviewing. That is, now when there are multiple criteria, question number 1 is how do you make the review system so that the evaluation along each criteria is better? And question number 2 that people have thought about is that now when a second thing that you have to look at is how the criteria are mapped to an overall decision. And there's a lot of arbitrariness here because you might emphasize novelty more and Jingyan might emphasize feasibility more, etc. And so what do you do about this arbitrariness? So in the non-randomization setting, there's things being done. I suspect some of it might carry over, but yeah, to think deeply about it. But if you're interested, I'm happy to, there's some very cool experiments that people have done on it, and I'm happy to chat about it.
I guess I'm just kind of thinking in the example where you're saying the bounds are determined by max, min, reviewer, if I was a sneaky reviewer and I wanted example proposal A to have greater chance, would it make sense that I would want to raise B's proposal high enough so that, or low enough, I guess I'm thinking what is the sensitivity to
that's true, yeah, absolutely. So in the max min, it's much more sensitive, right? And so if you raise A is high or B is low, then yes, it can significantly influence the output.
If you change one enough so that one dominates the other, does that significantly help them more?
Yes, so it can, and so if you care about it, you may not do the max min. You could do something like a bootstrapped confidence interval, things like that, which are more robust to these things. But on at a higher level, yes, you're absolutely right that this kind of a gaming is frequently possible. And that's where there is this very cool technique called what's called the partitioning method, which helps guard against it. That is, if your proposal is proposal A and you want to get it accepted, right? And so what you might try to do is kill competing proposal B. And what the partitioning method does is very cool. What it does is the following. It's a very simple, very cool idea. It says that, look, we have all of these proposals, okay, and then you have a pool of reviewers. Let's split the proposals at random into two groups. Now the authors of the proposals in group A are given to review proposals in group B. The authors of the proposals in group B review the proposals that are in group A. And then the decisions for both the groups are made independent of each other. And now no matter what you do, you can't affect your own proposal.
I have a quick question about this. So here it appears that the order is important. Like, you know, where you transfer mass, right, from kind of right to left, it's important what is the relative order of proposals.
Yes.
And so if like PI and PI plus 1 are really close to each other, then it really matters whether one is larger or the other. So it's not kind of continuous, right?
Yes, fantastic. That's a great point that you're making. And I'll illustrate that here. Like in this specific case, one solution for that is this is 3-4, this is 3-8, and this is also 3-8. And these two are very similar. So now what you're saying is absolutely true, that if you were to pick this versus if you were to pick this, then it can make a significant difference to which one you pick. Here, this kind of mitigated by saying that we can modify this algorithm and say that instead of transferring 1/4 from here, you transfer 1/8 and 1/8 if they're almost the same. And that will also work. So yes, you're making a very valid point.
So it seems like when we make the final decision, it doesn't really matter the joint distribution of like whether we select each proposal or not, as long as we are selecting K out of them, and we sort of only care about the marginal. I was wondering maybe there are some other criteria where we care about the joint distribution. For example, if like I'm someone who submit like, I don't know whether they allow, let's say I submit 2 proposals there, I might care about whether like both of my proposals go in there. So I was just wondering whether there are like certain criteria where it sort of matters the joint distribution.
Yeah, perfect. That's a great point. And yes, in many cases, in various cases, it will matter. For example, let's say you want a diversity of chosen proposals. You don't want all of the proposals to be selected on neural networks for X classification, right? Things like that. So you want diversity, and that's where definitely the joint distribution thing will help. And currently, it's a heuristic in the way they are employing this. That is, you can have different tracks, and then you do it in each track. But absolutely, I fully agree with you that if it's integrated here, it'll be much better. And that's something that we haven't done yet. Yeah, that's a great point.
All right, so let's stop here and let's thank Nihar again for the talk.
Thank you.